Hi everyone, Pinoy Bedrock Science here. I'm going to share to you how to manually compute and analyze Latin square design, data analysis, and field experiments. In conducting field experiments, the use of LSD or Latin square design is taken as N by N design in such a way that the rows contain the treatments once, and in column the given treatment also occurs once. It provides a two-dimensional blocking in such a way that two-way variations can be taken care of, meaning the bidirectional variation can be checked. The number of treatments equal to the number of squares or blocks, or the number of treatments equal to the number of replications. A common example is 4x4, also 5 and 5. That is the blocking design. Take note that the number of rows and columns are equal. The number of treatments are equal in its column or row, but there is no overlapping. For example, in 4x4 we have 4 rows and 4 columns. Any treatment occurs only once in a row and in a given column. This is an illustration of 4x4 LSD or Latin square design, where plots are assumed to be uniform in size and the treatments are distributed by rows and column without overlapping any treatment. This is a very standard format for 4x4. For a 5x5 design, we have, for example, the data collected can be presented this way. We have the columns 1, 2, 3, 4, 5, and we have rows 1, 2, 3, 4, 5. So these are the rows total, these are the columns total, and this is the grand total. Now let us analyze a sample. Of course, we start with the problem, and this is weeding frequency and yield performance of soybeans with the following hypothesis: null hypothesis, no significant difference; alternative hypothesis, there will be significant difference, or at least one treatment mean is different from the others. What are these treatments? We have control, no weeding, designated as A; B, frequency is once a month; C, twice a month; D, thrice a month; and E, 4 times a month. So those are the treatments. When we're done gathering the data, we present the result after computation, the analysis of variance, and this is the form of the ANOVA for LSD. The source of variation, we have rows, columns, treatments, error, degrees of freedom, sum squares, mean squares, and the calculated value or F ratio. By the way, this will be tested at 5% level of significance or 95% confidence level. For example, we obtain data on a 5x5 experimental design based on the problem, and we have the rows and columns. These are the yield obtained by columns and by rows. We have the column totals, and we have the rows total, and we have the grand total. The first step in the analysis is to calculate the correction factor. So we square the grand total divided by the product of the rows and column. So this will be 384 squared divided by 25. You obtain this 5,898 with 4. Then we have the total is S. These are the entries in the previous table. So we have 10 square, 1 square up to 3 square. Then we find the sum minus the correction factor, and we obtain 1625.76. The sum of squares due to rows, we have this rows total. We also do that with squaring. Divided by 5, we obtain minus CF, we obtain 14.96. Then the columns, we square this. The sum is divided by 5 minus CF, our correction factor, and we obtain 84.16. So these values will be summed up in the ANOVA. But before we go to ANOVA, we have to sum up all the values for treatment A. B, C, D, and E. These are the totals. So the total of treatment is A10, B 72, 115 for C, 120 for the 57 for E. When we divide the total by 5, we obtain this treatment means at the bottom. And we calculate the treatment is S, or sum of squares for treatment. We square this up to 57, the sum divided by 5, minus correction factor. We obtain 1 for 74.96. And the error due to the SS due to error, we have total is S minus row is S minus column is S minus treatment is S. We have 51.68. So we put them all together in the analysis of variance. So we have the source of variation, rows, columns, treatments, error. These are the degrees of freedom. These are the sum of squares previously calculated. And this number here is obtained by dividing the SS, or sum of squares, by the degrees of freedom. So this is divided by 4, 3.74. Likewise, this is divided by 4, this is divided by 4, this is divided by 12 for the error is S. So we obtain these values. This value is obtained by dividing the mean square treatment divided by the mean squares of error. We are only interested here in the treatment. We are not going to include in the discussion the interaction effects of rows and columns. So the ratio of mean squares for treatment over that of mean squares for error is 85.55. And we compare that with this tabulated value of 3.26. This is highly significant actually. So significant difference was observed, therefore null hypothesis is rejected and the alternative hypothesis is accepted because calculated F value is greater than the tabulated value at 0.05 level of significance. In this case, post-hoc test will be conducted. We obtain this 3.26 in the F table. The F tabulated value for F distribution, we have degrees of freedom for treatments. This is the degrees of freedom for error, and the intersection we have 3.26. Okay, it's here. Now, how do we conduct the post-hoc test? For comparative analysis, we start with determining the standard error of treatment means. And we have this formula, 2 multiplied by 4.31 divided by 5. So where do we get this 4.31? This is the mean squares error. divided by 5, number of treatments equals 1.31. Actually, this is plus or minus 1.31 after after extracting the square root. We only take the positive root, 1.31. Then we compute the critical difference. But first we have to determine the critical t-value under degrees of freedom of 12, and we obtain 2.179. This is where we obtain this 2.179. At 5% level and degrees of freedom of 12, the critical value is 2.179. This one. The critical difference is 1.31. Then we multiply it with 2.179. We obtain 2.85. This is your critical difference value. And when this value is greater than the mean differences between treatment means, there will be no significant effect between the treatment. If this value is smaller than the difference between two treatments, then there is a significant difference between the effect of two treatments. We can summarize that in the next table. Here is the treatment comparisons. So treatment B minus A, C minus A, the mean of B minus the mean of A. So we obtain this means, and then we find the difference. We obtain the differences between mean, and for B minus A, 10.8, 90.4, you will take note that the critical difference at 0.05 level here are less than the mean difference, and they are interpreted as significantly different. By the way, there's only one no significant difference noted. The difference is 1.4 and less than 2.85. By the way, these mean differences are all in positive values. I mean, these mean differences are taken only the positive absolute values. So when we write the result, we tabulate it with a summary of the treatments and the mean yield. By the way, this is 10.0, not 100. So by comparing from the previous table, we designate superscripts to indicate the significant or no significant differences. So those means with the same letters like C and D show that they are not significantly different from each other, meaning the effects are almost the same, but they are significantly different compared to A and B and E. Likewise, B, A, and E, they are significantly different. But overall, treatments C and D are the best performing treatments, and they are also significantly different from the rest at 0.05 level of significance. That's all, and see you on the next statistical video that I'm going to prepare. Thank you.